Hey guys, welcome to today's study group on section 24, regularization. So we're going to be covering quite a few different kind of topics today. And before we get started, per usual, I just want to open up the floor. Are there any questions or comments that people have on this section, or things that they wanted to revisit from yesterday's class, double back on? Anyone? No?
Okay,
All right, cool.
well, we can't have nobody say anything, and you can count on me always. My comments, having kind of gone through it, um, were to kind of focus more on the higher level concepts of what it is rather than focusing, when you get to the labs, focusing deeply on the code. Having spent one-on-one with you, kind of working through it, just understanding that there's more than one way to skin a rabbit.
Sort of
Um,
like the why of why doing it. Because I know there's one or two lessons where it's like a lot of code, and then sort of like, why did we just do all of that? What was the point? Kind of thing, like
exactly.
getting them. Okay.
So I got to the bottom of one of the labs and it says, now you know how to use Ridge and Lasso for feature selection. And I didn't understand what that meant. So
Okay.
if we
Good
could
point.
cover that explicitly,
Hmm.
it might help those that when they get to that part,
Yeah,
understand
absolutely.
why we're doing what we're doing.
Absolutely. Anyone have anything else? Okay then. All right. So today, now actually, interestingly, if you guys remember the extensions to linear model section that we did for Mod 2 when we first transferred over to this curriculum track, it was the one that had polynomial regression and had a couple other elements to it. That actually used to be all combined with this section as well. So this used to be all one giant section that you had to do all together. So I think it's a little bit better now that it's kind of spaced out, and we can digest these topics with a little bit more time to think about these. So the things we'll be talking about today. So we're going to be talking about regularization techniques. So we're going to both discuss ridge regression as well as lasso regression. And then we're going to discuss AIC and BIC values. And then we're going to compare different feature selection methods. And then we're going to have a good amount of practice turning repetitive code into flexible functions / loops. So there's a couple of good examples in the section lessons where there was code that was screaming out for simplification and for making more flexible. And I know that that's something we are in general trying to revisit and get better at over time. So we're definitely going to take a chance to get together today. And then, so diving right into it. So we're going to be discussing first regularization techniques. And so essentially, regularization techniques are basically ways in which we can shrink down prediction variables instead of actually deleting or zeroing them. And how do we actually do that? Well, we take advantage of what's called penalized estimation. And actually, maybe I'll move this up first. So if you guys remember from previous class, previously when we were doing our residual sum of squares cost function, this was the form that we were using, right? So we had, the simplest form, it was just here. It was, the error between each y and its prediction squared, summed. But then we had the multivariate form that we used with gradient descent when we were working on the last class's labs. And now, so this is something we actually didn't show last time, but this is actually what the equation becomes once you have multiple predictors. And actually, targeting back to that lab yesterday at the end, so I better understand their code now, seeing this form as to how they actually, why they've structured it the way they did with their sum in the middle of the for loop. If you guys remember who were here, but I just wanted to show that as well. So this is where we're starting from. This is the previous cost function that we've used for linear regression to judge how good our model is. And now we're actually going to introduce penalized estimations, where basically what we've seen previously in the prior sections is that when we have a large number of predictors, our model complexity is going to increase, and we're going to have a higher chance of overfitting. Now, instead of just deleting the actual predictors, so if you remember for your Mod 1 project, for example, we just sort of just figured out if there are multi-collinear variables, we maybe just eliminated one altogether, kind of trying to figure out which one, and just manually removing them from the data set, as opposed to having a way to, programmatically remove them in an intelligent way. And so the way we're going to do this is we're actually going to change our error functions, our cost functions, to get an altered version of those functions. And we're going to get what's called the penalized estimation. So ridge and lasso regression. So these are the two examples of penalized estimation. So ultimately, they're going to reduce model complexity. They may prevent from overfitting. That's not quite guaranteed. And then some of them can be performed to select variables. And then we'll be actually going through that today together. And then they can be used to counter multiplanarity as well. So yeah, with that, we're just going to go ahead and dive into the actual equations and kind of talk about what's actually going on here, what's added to these equations, how does it work, and then why would we want to use these. Okay, so this is our new cost function for our ridge regression. So ridge regression takes advantage of or uses L2 norm regularization. Now that term probably doesn't mean anything right now. So I'm hoping that at least you'll be able to start recognizing what these terms mean as we go forward after today's lecture. Okay, so you'll notice that up until right here, this is the exact same equation that we had before. Okay, so all of this is not new. What's new is this term right here. And so I have it isolated right down here. So essentially, we're adding an error term that has a hyperparameter called lambda right here. And that is going to be multiplied by the sum of the squared coefficients. And so basically, if you have a large coefficient, you're going to have a large penalty because keep in mind, this is our error term, right? So we're judging how good our model is with this function. And here, anytime we start to have coefficients that are large, they're going to be squared, and then they're going to be multiplied by this lambda value, and then added all together with a normal error. And that's going to be a penalized error due to this additional term that we added here. And this is going to help shrink the coefficients and basically help the model reduce complexity and multicollinearity. Now, not sidebar, just to zoom in on help with the terminology. So you'll notice that in this equation, we square the sum of our coefficients. So this square, this exponent of 2, is actually where we get L2 normalization coming from. So L2 is when the coefficients are squared. And then, yeah, so this is just the form of the equation. We have multiple predictors, but we can kind of just move on from that. This is going to be used to prevent overfitting primarily. And it can be very computationally expensive, though. So it's not necessarily what you're going to want to, go to right away. Versus we also have lasso regression, which is also uses the L1 norm regularization. So lasso stands for least absolute shrinkage and selection operator. And so once again, you'll notice we have the same basis to our cost function as before, except now we have this term added to our cost function. Now, once again, we have this hyperparameter. So remember, we used that word once before. Hyperparameter is basically any setting that we set for a model or sort of function from the start. So it's sort of us changing one of the knobs or dials on the various options for a model. And so lambda is one of these hyperparameters. And then this error term, though, you see it only has the absolute value of the coefficients. And so if you remember, when we don't have an exponent displayed, it really just means it's an exponent of 1. And so this is where the L1 norm comes from. So I'm hoping that hearing these things and kind of connecting which part of the equations are added will help some of this sink in the long term. So now this also will help with overfitting, but here's what it does that's special that doesn't happen with regression. So it shrinks the less important features coefficients down to 0. So it literally is going to wind up removing them from the equation because no matter what that column's data is, it times 0 is going to be 0. Therefore, it won't be used in your model. So this would be a way that we could select features for our regression by allowing the model to basically determine which ones are not worth it and which ones should be dropped out of the actual model. And so questions on these two different equations and two different types of regression before we move forward with applying them. Mm-hmm.
I want to clarify the coefficient not being squared or take an absolute value from your regression line for as many terms as you have.
Sorry, can you say that again? You broke up a little bit in the very beginning.
So coefficient you're like doing the squaring to or whatever, that's the coefficient that you use in your regression formula.
Yes.
Okay. Okay.
Yep. So that's basically every coefficient that you have for all of your x terms. You're gonna basically square all of those and sum those up. Yeah. And so you see that that really would add quite a bit of a penalty, right? If having those actual values squared, that's going to make this, you're going to get a much larger error than you would have gotten if you did not have this regularized version of the regression. Do you have a question, David? Nope.
Nope, I don't.
Cool.
So I guess the quick question is, so this is another form of linear regression?
Yes. Okay. Yes. Yep. So these are two new flavors of linear regression. And then, yeah. So okay. So when we actually want to use these, a couple important points. So since we're relying on the math to drop out the coefficients, especially with lasso, it's really important that we do have our data standardized before we actually go to do this. Because if we have very different values for each column, that means our coefficient value is going to be from a very different range. So it's unfairly going to punish columns that have large values. For example, on the Mod 1 project housing set, remember how we had square footage versus number of bedrooms. So if you didn't actually scale those, square footage went up to like thousands, whereas for bedrooms we had I think at most like 30, which was I think might have been an error. So we really had like 5, and so just by the units of the data themselves being larger, you would wind up penalizing square foot more just because of the fact that the units are larger for that. So that's why it becomes more important now to actually make sure that you standardize your data before you run these regressions. In this case, the lesson uses, and I probably would steer towards using min-max scalar as opposed to using standard scalar, because min-max scalar is guaranteed to all be in the same range, whereas when you do standard scaling, it's going to be based upon the mean and the standard deviation. So usually it's between -3 and +3, but not always. And so that is not necessarily going to help you have that standardization you need to let the math fairly judge as to which columns should be dropped out versus the others. Okay, and just just recapping. Remember, so this is really all that's changes between linear regression baseline version and Ridge or Lasso is really just changing these error terms so that we have this additional penalty added depending on what our coefficients are. All right, so we're going to move on, and we're actually going to apply this with scikit-learn. So this starts at especially from one of the lessons directly. And so we're going to go ahead and load in the data. And then we're going to use our min-max scalar. And so we will be doing a lot of coding together live, but at this very beginning, these are just copy-pasted cells from the lessons. So we're just kind of let it go through these first. Okay, so min-max scalar, right? And so here's an important point that I'll definitely hammer over time, is that when you have training data and test data, and you want to scale it, you don't want to fit transform your test data. What you want to do is you want to fit transform your training data. So you want your scalar to only learn from your training data, and then you want to just transform your test data. Otherwise, you can get what's called sort of leakage, where basically if you scale the data with all the data together, then the numbers that you feed in to teach your model are already biased and altered because of the data that it has not seen yet. So you sort of create an issue where the actual relationships between your training and test set will sort of already be, it'll be sort of baked into, I don't know how to specify that. Just put this away. It's basically just going to cause a lot of unnecessary, the values in your test data are going to alter your training data. And that's not what you want. You basically want your model to be able to be trained on one set of data. And then in the real world, you want it to be then able to be applied to data it's never seen before. So if we scale all the data together, then we're already biasing the actual range of values for that data. And that's not, you don't want to do that. So yeah, important point that you'll see over and over again. Just wanted to go ahead and make that explicit now. Okay, so these three, so this big block of code, this is from the Ridge and Lasso regression lesson. There's originally 3 different cells, and I want to talk through. So this is going to be our case for why making functions and using dictionaries is worthwhile, and how it can improve our code and make it much more flexible and shorter. And so we basically, this code, what it's doing, it's creating a ridge, a lasso, and a linear regression, a baseline one, and it's fitting all of them. And then it's getting the predictions for each one and storing them in a separate variable. Now, we will come back to this in a moment, but you'll notice there was a question on Slack about why there's this reshaping and why these values. We'll touch on that more in just a moment, especially if other folks have that question. But just for now, just take note that in these lines, they're just getting predictions for both their training data and their test data for each of their models. And then now here in the last cell, what they were doing was they're basically getting their sum of squared errors. They're basically for each of their training and test data sets for each of the three models, and then reporting the coefficients. So you see that in order to compare these three different models, there's a lot of lines of code that are basically doing very similar things, if not identical things, that we're sort of having to copy paste and then remember a whole bunch of different variable names, and do a whole lot of print statements. And it's just it's a lot of code that what if we wanted to add another type of model to this? We'd have to copy and paste each individual section of this process and update all the variable names to match that new type of model that we're making. And that's just very tedious and inefficient. And so originally what they're wanting us to take away from this is looking at how comparing the ridge, lasso, and normal baseline regression, how they basically error terms change. And in actuality, in this lesson, they acknowledge that for right now, they actually don't change very much at this point in time. But so, okay, so question for the group. So what are some of the issues or limitations? And I gave a little bit away already. So what are some limitations in the way that those three models were tested and compared above? Who's willing to take a stab at it?
Well, is it all based upon the error? We are squared as another way to evaluate models' performance.
So break up a little bit. What I think I heard was that you're basically saying that they're not using something like R squared to evaluate the model's performance.
Yeah, that's just it's a different metric. I think that could be used separate from error.
I definitely like that idea, and we're definitely going to work on that. But it's not quite the issue that's kind of going on here. Andy?
Well, I was going to say you have to, in my mind, you have to scale it. You have to scale everything and normalize it. I don't know.
Well, so that thankfully is all done up here. So that's actually done before this process, right? So there's basically two issues on this page. So the one we were just talking about a moment ago, which is basically that if we want to add another version, another model to this comparison, we have to copy and paste a whole lot of lines of code and do a lot of editing. And that would be the main drawback, I would say. So if we wanted to add anything, like add another model type, we'd have to copy a whole bunch of cells, and then we'd have to edit a lot. So copy a lot and edit a lot. And it'd be easy to make mistakes too, because you might forget to change one of the variable names on one of the lines you copied and not another. So that's one issue. There's one other issue up here that is very inflexible in this block of code that, in my opinion, that we shouldn't know. Andy, I know you know the answer. So we talked about it already today. So someone else.
Oh, I know where you're going with the question now.
Yeah. Does anyone else see anything in this cell? I'll give you a hint. It is in the middle block. As to something that just is very rigid and would not, if anything changed in our data, our code would break because of something that's on the page right now.
Well, you have to reshape it, right?
So we think we'll always have to reshape it because of what Lasso puts us out. But what are these shapes in the first place, right? So let's go ahead and talk about that. So these are actually the shapes of our training and test data. And so they hard-coded in that they wanted to reshape it to match this. Now, why do that when we could just do this And then now, no matter what Y test or Y train becomes, we're not going to have an issue because it's exactly pulling from what it needs to match, right? So they're creating a new version of the prediction for the Y train, and therefore they want it to match the Y train shape. And so that's a good example of times where if you ever see hard numbers coded, especially in a lesson, it's a good time to practice thinking about where do those numbers come from and how could I programmatically grab those instead of hard coding in those numbers directly. Okay, so yeah, that was basically yeah. So hard coded shapes. Steve got a chat. Thank you. So hard. Where was I missing the parentheses, Andy?
Where you modified the numbers, so line, what is that, 17, 18?
Yep. Wait.
Right,
So that's the
right before Y train shape?
in here?
No.
No, I need that.
So
No,
there,
that was all right.
you don't need that?
No, oh, sorry, I do need that one. Yeah, you're right. So which one you're saying?
No, not there. Yeah.
Down here.
Hey, wait.
When you see a line number, tell me what line number.
Yeah, line 17 and 18 where you were. When you changed it, right, and you put in Y train shape, I swear it had brackets on both sides of those.
So I think if it pandas data frames, I think when you get the shape, I think maybe then you have to use commas, but you don't have to normally. So we don't need those. It's an attribute, not a method. Therefore, we don't need to use parentheses to call it.
My bad.
You know, good question. Good thing to discuss for sure. Okay, so hard coded values for data shapes. All right. So we're gonna make this better. We're going to, as a group, we're gonna make a function that's gonna handle all the repetitive tasks that are happening for these three different models above. That way, we could use that function to get results for any given model, and we could just churn that out in a for loop with a list of models. And so there's three different components. Okay, so we have a starter code first down here. So I have this. It takes a sklearn model and a train test data. So basically X train, Y train, the whole all four, and then it's going to get R squared and actually going to be root mean squared error for both the training and test data. So they technically up here they were just doing RSS, but we're gonna do root mean squared because they basically just did the sum of the squared errors. We're gonna go with root mean squared error. And so we basically now want to turn this process above into a function. All right, so does anyone, okay, so let's do this. My recommended step, whenever you want to start making a function that's based on code you have in front of you, I say we pick one example of the code being used and combine all of its lines in that cell where we're making our function, and then we can edit it then and modify it to make it more flexible. So we're going to need, let's maybe use the ridge model as our test code. And so we're going to paste in the first lines of this. And so we are then going to get its predictions. And incorporate. There we go. And then, yeah, so this Wisp will come up again, this reshaping thing, but we'll deal with that shortly. And then we're going to want to get a couple scores. So we don't want to just get error. We're going to get R squared and the root mean squared error. So to do that, we're going to have to take advantage of some functions from scikit-learn.metrics. So for right now, we can kind of take a step back and think about, okay, what am I using so far inside of this function that I'm going to need to provide as the user. So we obviously have our model, but we want to have the model be like whatever we fit in. So we don't want it to actually be created inside of this. We actually want it to be provided. So the model would be our first parameter, and I'm going to change bridge to model just so now it's in a more generic form. And then we know we're also going to need our training and test data. And so I'm actually going to go for the generic names, the original ones from because that's more traditional. So I'm going to paste these in. And then now I think we would have everything that we need to finish executing what we want. So
James, question. But at what point further up did you break these did you break up the data set? What is it, 80-20 or 70-30 or?
Good question. So I think I left with whatever the lesson used. It used a 70-30 split.
Oh, okay, okay, so, all right.
Yep. So good question. All right, so now let's go ahead and we don't have X train transformed, we just have X train. And let's simplify this to just Y hat train. And we need the same thing for this line, but for the test data. So just change train to test. Okay. And now we have our predictions. Now, what do we want to get next? So I'm opening this up to the group. We wanted to ultimately get some values to report back. Does anyone have any suggestions on what we should do next in our function?
Well, you want to check the accuracy, right?
Yep, we do. All right. Yep. So I'm on board with that. Let's get some R squared values. Sound good?
Yep.
All right. So let's go ahead and get R squared for training for our training data. Here I'll be more specific. R2 train. And so we're going to use R2 score from scikit-learn. And something you guys will come to learn very soon is that scikit-learn is very standardized. So almost all of their functions that are used for metrics all take basically the same parameters. And why? Oh, I haven't run it yet. That's why. Okay. So just a reminder, until you import things, sometimes the doc strings won't pop up. So you see, for R2 score, all it wants the true data and the predicted data. And that's basically all we need to provide. So we're going to go ahead and do that. So R2 score, our true data is the actual Y train that we've actually provided and passed into the function. And then our predicted data is Y hat train. And then we want to do the same thing for our test data. So we'll make this R2 test. And then this is Y test and Y hat test. And then, okay, good. Now we have some accuracy scores. Now, we haven't actually done anything with them yet, but we could either maybe worry about that later, or we can worry about that now. Maybe let's worry about that later. Let's worry about now getting error. So we want to do root mean and squared error. So how do we do that, taking advantage of some of the functions we've already imported at the top of this cell?
It would be the same thing, wouldn't it? But just with mean squared error, as you do with
close. That would give us mean squared error, but we want root mean squared error. So remember what we do to get that?
NP square root around that?
Exactly. So we take the square root of mean squared error. I'm actually surprised scikit-learn doesn't have an option for that, honestly, because it's so popular. But, to each their own, I guess. Okay, so we're going to get the RMSE. And so that's going to be, once again, it's just going to be the true training data versus the predicted training data. And so we're going to do the same thing again, but now for the test data. Okay. All right. It's looking pretty good so far. So the last thing that I'd say we want to do, you guys who are usually coming, so me, I really like making things ultimately into a data frame. And I usually have kind of a technique that we kind of do a lot. So I recommend that we make an empty results list. Okay. And then we are going to add for each of these pieces of data, we're going to have the data type that we had, so whether training or test. We're going to have our squared value, and we're also going to have our root mean squared error. And so we're going to make a list that we're going to keep appending to, and then turn into a data frame. So here's going to be our headers later on, and then now we can actually down here we can append what we have to our list. So res.append, and then inside here we're going to be appending. So for our training data, we're going to fill in since we're doing R squared next, we would fill in R2 train. And then since we're doing root mean squared error next, we'd fill in root mean squared error train. And then now we just do the same thing for the test data. So I'll make this test. All right. And then finally, we're going to use pandas to turn this into a pandas data frame. Now, does anyone remember how we take a list like this and turn it into a data frame in one line of code? So without having to generate column names elsewhere or anything. It is using pd.dataframe.
PD to list or?
So we're gonna use our list. So what we want to get, basically our data is going to be from our res list. However, we don't want the first row because that's actually going to be our headers. So we're going to say we want res 1 to the end. And then we're going to say columns equals res of 0, because that's what these are for. Now, the reason I like doing this, especially for a process like this, is that it spells out at the top of the process for yourself what needs to go in each position. So it makes it a little bit easier to keep track of that as you go, as opposed to doing it later on. Okay, and then that I think should be all that we need. I don't think there's anything else in my. Oh, yeah. Okay, yep. So there's actually 2 things that we wanted to return. So here, save this. This is our results df. And then the other thing that our function we're going to return is going to be our actual model, our fit model. Now that this version of the model knows the data, so we're going to return our resdf and then our model. Okay. So let's actually go ahead. I thought I actually had a cell saying test it. Let's do that. So let's test our function. Okay. So we want to make model. Actually, we're going to have a df results and the model itself. And we're going to make a model. Let's make a linear regression. So we're going to go ahead and just initialize it right here. And then we're going to need our train test data. So I'm going to go ahead and be a little lazy and copy this right here and paste that in. And so that, if everything works properly, should have worked. And then what do we get? All right, let's go ahead and maybe, so we're going to have probably a lot of gnarly values. They're going to be very small. So let's go ahead and add a dot round inside our function just to keep things a little bit simpler. And even then actually didn't really round. Interesting. Oh, because it's so big. Ah, okay. Wait, no. Something's not right. Minus 6.7 times e to the 9th. That seems a little odd. I'm just double checking with what I did previously. Mean squared error. Yeah, that's what we did. Oh, give me some square root. Well, I think it's technically okay. It's just a little surprising. So let's double check what I did here. So we got our model dot aha. So this is once again a warning about writing functions inside a notebook and remembering that functions can actually access data outside of themselves, which is very different from when you write them externally. So what was happening is it's actually using this xtrain transform variable, which is actually not what we're using. So we're actually using xtrain and ytrain. And so I believe, yeah, there we go. Those are numbers that look normal. All right, there we go. That makes a lot more sense. Okay, so now we're able to, in this one function, feed it a model and get back all these evaluation metrics in one data frame, as opposed to having to type out, all this separate code and all these print statements. And so now that we have this function, we can actually try out all those 3 models that they were doing above, but we can do it in using a dictionary and a for loop. So we're going to go ahead and we're going to make our model dictionary first. So we're going to call this models to make. And then the whole point of this section is to compare the linear, ridge, and lasso. So we're going to make, this is going to be equal to dict, and our linear model is going to be equal to our linear regression, and our ridge is equal to ridge. And then I believe they had a parameter in the code, I think alpha 0.5, I want to say. Yep, alpha 0.5. All right, alpha 0.5. And then just one more to add. This is going to be lasso equals lasso. Alpha equals 0.5. And I believe that should be all correct. And so now inside this dictionary, we have our models to make, and they're stored under their keys. So we have models to make, and then we have our linear model. Here we go. There's our object inside of our dictionary. And so, we could very easily just use the same function, just pulling out directly from a dictionary. Basically, that's what we're going to wind up doing now together. So this is where the big group effort is going to come in, because this next cell, this function has set us up for this. Now I have a pretty good pseudocode outline for us here in terms of how we can actually now use this function with this dictionary to try out all the models and get results for all of them like they did in that block of code above us. So, all right, so there's actually nothing left for us to do in this first thing. So we're ultimately going to be looping through all the models and saving the results. So we basically first need to create an empty list to store the result data frames. So I'm kind of thinking we call it results. If anyone opposes that, by all means. And then we also want to have a dictionary that we're going to store the fit models back. So I'll also get this one going. We're just going to call it fit models. That's going to be an empty dictionary, right? So just curly brackets alone. All right, so now, if you guys remember, with our dictionaries, we can use .items to loop through both the keys, which in this case are the name of the type of model, and the models themselves. So how would we then, now that we have our model type and our mod, so how would we actually use our function? What should we do in this next line of code here?
You would have function made.
Yep, so make model. And then what would I feed in here?
Mod.
Exactly. Because mod is actually the model object that was stored as the value in our dictionary. And then once again, I'm going to just copy paste these. Okay, cool. And then, but now we haven't actually saved the outputs yet, right? So do we remember what we get back? So thankfully we wrote ourselves a little doc string, right? And so we're going to get back both our data frame and our model that's been updated. So I'm going to say res df, actually just res, res equal, and then res comma mod equals make model. Okay, and now res, if you guys remember, actually, so from up here, when we ran this is actually a data frame. So right now, if we're doing a loop, right now we have all the stats saved, but we don't have any representation as to what model this came from. And so if we're going to have all these, it'd be nice to be able to keep track of what model we're actually representing with those results. So we want to add a column that contains the model type to our results. So how would I do that with the res variable? So we want to add a column and we want to fill it in with the name, the type of model.
Say res bracket, what are you going to call it? Type.
Okay.
Equals.
Mm-hmm.
Anyone can help me that wants to. My brain just stopped.
Okay. Okay. No, and this is purposely.
Pull from. Where is it pulling from? Is it the dictionary?
So all of this is being pulled from the dictionary.
Yeah. So pull from that same thing, right?
So what would I pull?
Items. Can I see models to make again?
Yeah, absolutely. Oops. So models to make is going to be the dicts.
Yeah. So it'd be item, or it would be keys.
Uh-huh. But so do I already have that though?
No.
Are you sure?
Well, you just printed it up there, right?
So we're looping through the items of this dictionary, which means that we got both the key, which is the type of model, and the model itself right here. So to fill in this column, all we need to do is use this variable. And that was purposely meant to be like reminding us that we can actually get those, use those keys that we're pulling out to actually be able to fill in data and help keep track of things. So that was kind of purposely put in there for that exact discussion and realization. Okay, and then we're going to want to be able to see the results in the middle of this loop. So how could we get that to, how would we be able to see the results of our res right now in the middle of this? There's two ways, one of which is better. And I'm curious, so there's one command you guys use all the time, one that I'm encouraging you guys to use more and more. And so anyone have a stab as to how you want to display this data frame?
Show res?
Actually, is show a thing? I don't know if show is a thing. Let's actually see.
You know the right thing?
Okay, no. You're getting close.
Display.
Print.
Display, exactly. So
Printer
remember.
display.
Sorry? What was that?
Oh,
I couldn't hear the last person.
right?
Now the reason that's better, right? So let's go ahead and take a moment, because this is a point that I will make more as you guys, because this next project you're going to want some nice high quality results to print out. So if we were to actually have just printed out, so here we have our results, right? DFRES. So if we were to have printed instead, we get that, and that's gross. There's no, like, we don't want that. So display is going to give us what a data frame should truly look like, and that's why I highly recommend display. It actually is much more easy in the eyes and easier to read. Okay, so we want to save our updated fit model to our fit models dict. So how would I do that? How would I fill in this fit models dict with that model? And also, I should say, I want to be able to keep track of which one it was, so I want its keys to match.
When you would append your dictionary.
So I would add it to my dictionary, but we don't have a pen for dictionaries.
Right, you don't have a pen for dictionary.
Mm-hmm. So I had to fill in a key of some sort.
Would you do fit model, the model type in square brackets, and then equals the model itself?
Bingo. Exactly. And then finally, we want to save our data frame to our results. In this case, it is the simple dot append that we were just thinking of, because this is just a list. Okay, so we're just going to append our res, and then we're going to be able to get all the models results. And then let's go ahead and let that run. Oh, what did I do? Oh, fit models. My bad. Okay.
For that variable, I was like, where is that?
So now this is pretty good, but in reality, I'd like to be able to compare them a little bit better. So the reason we have all these in a list now, so if you remember, whenever we want to concatenate things, we have to feed in a list, but we already have a list. So we can just concat results, and bam, there we go. We have all of it combined into one big data frame. So dsres equals s. And then now it's easier to make this a little bit digestible. We can do things like setting the index, and we're going to do is multi-index. That way we can more clearly see the data. So we want to have the type and then the data as our index. And so now it's a lot easier to look at this and see, okay, so we have our linear regression here. We have our training and test scores. Here we have our ridge training and test scores, and then our lasso training and test scores. And so one last thing, I'm going to also start introducing to you guys more over time Pandas styling tricks. So we're going to use styling to make it easier to find the best scores. So this one I'm going to walk us through. I'm not going to expect you guys to know this one yet because we haven't talked about it. But any data frame, we can add a dot style on the end, which opens up a whole new set of possibilities for us. So what we want to do is we want to find where do we actually get the highest R squared. And so we're going to do style dot highlight, if it'll actually cooperate. Okay, now I'll type it all out. Highlight max. And then we tell it what column, which is going to be R2. Oh, did I not name it properly? Oh, DFRES. My bad. A little dyslexic. Oh, I did it again. Wait, no. Yes, DFRES. Okay. All right, now it doesn't like. So dot style. Oh, yes, that annoying thing. Okay, so we actually have to save this. So be in place equals true. And then I think we're fine. Yeah, okay. So this is one of many styling.
Nice.
Yeah, and this is just a very simple example. So basically, what it did, it highlights the maximum from the column I told it to, and then there's also highlight min. There's also much more sophisticated versions of these things, which we'll also do a little bit of shortly. Now, one of the things we could have also done, say we had a lot more values we want to compare, which we will when we get to the later section. We could instead of doing highlight max, we could have done dot background gradient, which then basically applies a gradient to each column, and then basically it's highlighting, in this case, by default, highlighting the maximum. So in this case, we probably would only want to run this actually in R2 as well. Oops, not R at. Oh, subset equals, I think. I think this one's a little bit pickier. And now Panda styling is something that not many people take advantage of, but they really should. And I think you starting to implement it in your projects and your reports that you have in your project will give you guys a very professional look for when you're applying for jobs. So that's part of why I'm introducing this now. Okay, so it looks like, honestly, and they kind of acknowledged in the lesson that like we really didn't actually get much more improvement in our actual model yet. So far, but at least we've been able to demonstrate at least up till now, that how they work. But importantly, we want to take a little better look at what happens when we actually have those coefficients that drop out. So remember, that was one of the special things that Lasso can do for us, is actually drop out those coefficients. So, so we want to examine the coefficients of the model. And don't worry, I promise, we're only doing this together up till a little bit later, and then after that, the code's already there. We just kind of talk through the rest. So the whole class is gonna be like this, just to let you guys know. So we want to examine the coefficients for one of the models. So let's go ahead. So where would we find the coefficients for one of our models that we just trained? I can scroll up to help us remind what we just said.
In the fit models dictionary.
Yep. Anyone have a preference as to which one we look at? No? Let's try last time. And then, so that's our model. Do you remember how we get coefficients from a model?
.cof_.
Exactly. And so here we go. Here are the coefficients for that one model. But now, however, we ultimately want to get them for all the models, right? And so we're going to do, so I know you guys have heard of, and I've done a lot of list comprehensions. So there's actually also a thing called a dict comprehension, dictionary comprehension. And so we're going to use one to get all of the coefficients from our models. So what we're going to do, we're going to go ahead and say, we'll save it just so we can reuse it. And so just like a list comprehension, we start with the empty brackets. So in this case, it's curly brackets for a dictionary. And we want to have the key, not capital, key and value, and key, actually, I'll do this, the key and model for the key model in our fit models, items. And now what we actually want, though, we don't want the model itself, we want the model's coefficient. And so by doing this, we are able to pull out all the coefficients from the 3 different models, and now we have them sort of in one dictionary. And then, but now there's a little quirk. Actually, did it show up this time? Let me try running above one time. There is an issue. So the reason that they had their the reshape in one area above, I thought we would see that showing up here. I guess not yet. Okay, fair enough. All right, so I guess that's the train test split. Well, anyway, so we're gonna go ahead and just check. Yeah, they all look the same. Before they weren't, I forget, I don't know what chain, maybe the train test split. So we were just going to double check the shapes, okay, so if we did want to print out the shapes for each of these models, their coefficients, how could we now do that? Once again, we're taking advantage of dictionaries. This could be a very traditional loop. It doesn't have to be anything fancy. For
shape.
For shape, okay. For
Yeah.
shape, what?
Oh, shape.
So remember, we want to get the shape for the our coefficients are arrays that are stored inside this dictionary right here. Also, in this class, I'm be very intrigued to get your feedback on whether or not you're liking this or hating this right now, or a little bit of both.
We're growing. Well, I am. It's okay to be uncomfortable. For shapes, print out the shapes for each dictionary.
Value.
I don't understand. What you mean by shape, because in my mind I'm thinking of like a or like NP shape. Yeah,
that's what I mean.
Yeah.
So we need to get it from every item, right? So I'll give us a little help here. So once we're gonna go for every key common value in our dict comp items. Now we could print, I just got my colon. We could print, and I'm gonna do an F string. I could say key shape equals, and here we can say v.shape, and I think that's all we need actually. Okay, and actually they're all the same. That's actually really surprising. So when I did this earlier, did I change data sets or something? Because normally earlier, like they had up here, the actual shapes don't come out the same, but okay, maybe that'll happen later. Anyway, now normally that we would actually get if that was the case, we would get an error here, but actually I think it's gonna work fine. So we're gonna actually might not hit what the doc string says we would. the comments as we would. So dictionaries are really, really, really easy to turn into data frames. That's another point that I wanted for us to get comfortable with. So bam, there. So actually, something's wrong. Okay, something's wrong. I thought it makes sense. Something is wrong because look at this. All of the columns totally match, right? So something went a little bit awry. And let's see.
I was wondering in your for loop right there. Wait, go up one. And this might just be an Andy thing. Wait, go back down.
Probably was up in that one, I would imagine, but
value. Okay, so there it says K.
Oh, ha!
And K.
Good catch. Good catch. Very good catch.
I can't believe I understand it.
Aha! And there we go. My example works again. Okay, thank you. All right, sweet, great. Okay, so we hit an error, okay? And the error was data must be one-dimensional. So if you guys remember when we were talking about linear algebra and getting used to matrices, so we talked about how could be one-dimensional or two-dimensional, and beyond that as well, matrices. Now, if you notice this, for both our linear and our ridge regression coefficients, they are two-dimensional shapes. So they have 1, 6, whereas our lasso came out as just 6, a one-dimensional. And so we need to be able to address that if we want to be able to combine all these back. Now, what the one option would be to do a dot reshape and try and match the shape of the other ones. However, there's a much simpler way that we can do that, and that solution is dot flatten. So I'm going to go ahead and copy our earlier data comprehension, and we're going to use that as a starting point. And then all we have to do is add dot flatten on the end of this. And then that is basically going to take care of the issue that we had. Bam. So what it did was it took all of those other ones that were 2 dimensions and flattened them down to 1 dimension so that now we could actually put it all into one data frame together. And so now really all of this I actually originally did, and I encourage you as you get more used to Python and comprehensions to actually do all of this in one line of code because there's no reason why we couldn't. And as long as it doesn't stretch the point of understandability, like you can still tell what's going on, then usually it's just fine. And so we can call this df coefficients, coefs, and that's gonna equal this. And then one thing we don't have though right now is we don't have the names of what these variables are. So where could we get the names of these variables? So remember, these are just our x variables, right? So we want to know which one's which. So where could I go to grab that information? So our columns are going to be equal
to the keys of that dictionary.
It's actually no, actually not the keys. You have to remember those are our models. It's actually not too difficult. We just need to go back to our x data. Because remember, and actually this is something that's nice. Nowadays we actually get data frames back from pandas, which is fantastic. So our x train has all the column names we need right there. So we can just say xtrain.columns. And then bam, we now have oh, almost. What did I do? Oh, no, that's right. pd.dataframe. Huh, what did I do? Columns equals xtrain.columns. Huh, 1 second. Let me look at what I have from earlier, because yeah. Coef, yeah, okay. So, sorry, where'd it go? Yep, pd.dataframe. Yep, okay, yep, yep, .coef, flatten. Yep, that's fine. I know what I did. Okay, so I actually wanted the index to be the columns. So that was the issue. So basically, now we're fine. Now, however, we're gonna do one last thing before we think about this to make it a little bit easier to compare. We're just gonna go ahead and take the transpose and then round it down. And here we go. Now we have the coefficients from each of the 3 models. Sorry, go ahead. Yep.
Why are you transposing them?
That way we have essentially, we're kind of looking at the equation again in a way, right? So now we sort of have y equals cylinders times, x times. So these are now basically the coefficients in our equation laid out horizontally. So I thought it'd be easier to think about it that way. And so we're seeing each model. So for each type of model, we see what the resulting coefficient was. And so one of our final discussion points, one of the things we're looking to learn here. So what was the result of these three different regressions on our coefficients? Can anyone notice something that's different or unique about one of them?
Horsepower is all 0.
Well, yeah, but it's 0 for all of them, right?
Mm-hmm.
Lasso has 3 zeros in it.
Lasso does have 3 zeros. Remember, Lasso is the one that will shrink unimportant coefficients and drop them out of the model. And so this is us being able to see that, so we can actually see which coefficients it basically shrunk down to the point where they're no longer going to have an effect on the model. And so now we can actually just kind of visually see and compare that. So yeah, exactly. So Lasso regression shrunk the sum of the coefficients down to 0. Okay. Very, very nice job, folks. Okay, so that I hope you guys enjoyed to a certain extent that activity. I think those skills of taking rigid code, refactoring it, turning it into functions, and being able to do it flexibly, that's going to serve you guys really well for your next projects. And so I know I kind of talk about how important that is a lot. So definitely want to walk through it together. So we're gonna talk briefly. So I want to say for understanding AIC and BIC, for now, getting used to the idea that these are two new possible cost functions that we can use is really sort of the main takeaway, but we're still going to kind of talk about how you can use these. So basically these two different values, so I always mispronounce the gentleman's name. I want to say it's Ikike, I can't remember exactly, but basically his information criteria, AIC, and also the Bayesian equivalent, BIC. So these are new cost functions essentially that we can use to compare models. And they're going to be ones that are not going to be set values. So it's not going to be like R squared where we know for a fact it's between 0 and 1, and therefore we can judge how good it is just by staring at it. These are going to be numbers we have to use relatively speaking. So we can always see if one model is relatively better than another. We're not going to have an absolute score from this that we're going to be able to make a firm conclusion on without making a comparison. And so now the lesson is going to show you basically there's two different versions of the equation. So this is essentially the simplest. You're really not going to be asked to really apply this directly. So just understanding that essentially what it's doing, it's essentially looking at any model that uses maximum likelihood estimation can basically be calculate AIC. And then this is essentially the equation you do so. Now you're not going to be calculating it directly. We're going to have it calculated by scikit-learn. So if anyone wants to dive deeper into the math and 101s, totally happy to. But in terms of what you actually need to be able to understand and apply, just getting used to the idea that it's one way, it's one new cost function that we can use to compare models in a relative manner. And it basically, it does use maximum likelihood estimation, which we're going to be revisiting, I think, next class. And then the likelihood. So technically log likelihood, basically it's going to use those to give this metric. And then the equivalent for the Bayesian equivalent is very similar. It's just with the slightly different, and it also can be used for the same purposes. And so we're not going to worry too much. Now, I just wanted to show you these two blocks of code that way you're not confused by one of the labs. So I think the very last lab I want to say, or maybe the original mouse regression. So they're going to have you basically have two different models. So what we have here, so we have in our linear models part of that scikit-learn, the same place we got linear regression from, and then lasso from. There are these other types of lasso regression which are actually cross-validated objects. So that's what CV stands for. What's important though is this, especially this one, we're going to be able to use this one to control and test the values for alpha. Because if you remember, we actually set our model's alpha values at the very beginning and never tried changing them. At the very first thing that we did when we made them, oh, check this scroll past already. Yep, here we set them all to alpha 0.5. Now remember, that 0.5 controls how much penalty we actually get from our coefficient. So that is something that we can tune ourselves and could have a very big effect on the quality of our model. And so that's one of the reasons why we have classes such as this that let us actually do sort of automatic testing of all the possible options. So we're using Lasso Lars IC. What the Lars and IC stand for, I couldn't easily tell you off the top of my head. I know that Lars is a type of algorithm, and I'm not sure what IC stands for. Oh, I guess information criteria. Yeah, that makes sense. All right, fair enough. So what this one does, it lets us specify what criterion and our options are AIC or BIC to use for it to automatically figure out what alpha we want to use. we actually don't even need to tell it which ones we want. So actually, that can come in now. It's literally just going to figure out intelligently all the possible values we might want to try, and it's going to come back and tell us which one was the best. And we're going to do this for both the AIC as well as doing it with BIC. And then, okay, so you're going to be asked to plot in one of the labs. And they're going to have referred to this link in the leading up to that point. Basically, you just need to go to that link and copy that function, because there's no way you would think to create this on your own. So don't think that you should be able to conjure this up without having gone to this link. And they literally just basically want us to go to the documentation and see them discussing how it's used, and basically just see how to plot it. So here we can actually plot and compare what we get for our tuning. So basically what it did, so it tried out a whole bunch of different values of alpha, which we have represented down here. And then here we have in blue, we have our AIC values as it changed these alphas. And then we have the BIC in green, and then it has the best values that it found, and actually labeled with a line, which actually wound up being the same with either method. So either method returned back 0.0015 was our best alphas that we should use with lasso regression with this data. So just so you know, we won't be confused when you get to this part in that lab. Just know that you have to go to that page, find that function that they use there, and go ahead and just bring that back to your own notebook. All right, so feature selection. We're going to go, let's do this. Times 808. Okay, so let's do this. We are ultimately going to, so this lesson is a very interesting one in that, all right, I have it right here. So it goes through a sort of general overview of different types of feature selection. Now, feature selection is really just any way that we can sort of intelligently decide what columns we want to use in our data set. Now, I actually forgot, I do have, I believe, so feature selection basically said is the process of selecting a subset of relevant features. And then why should we select features? Basically, we're going to make simpler models, so it'll be shorter to train, and then it'll be more generalizable. Really, what I wanted to get into was this overview here, which gives us a little bit better overview than the lesson does, in my opinion. So filter methods are one class of model, feature selection. And so they're going to select variables independently of the machine learning algorithm. So they basically rely only on characteristics of the data. And so we're going to apply one of those momentarily. And essentially, usually that involves having some ranked features, basically, with some criterion. And then once they're all ranked, then they actually select the highest ranked features, and that's what we use. The AI, well, I need to figure that point back. And then, yeah, we don't have to worry about that so much. Let's actually look at then, should I have the other ones in here? Okay, well, there's two other classes. I pulled that from a Udemy course that I do recommend. I thought you went into the other ones too. But anyway, so there's also wrapper methods, which basically would be selecting different subsets and basically keep trying them over and over. Now, recursive feature elimination, which I think they covered a little bit in the first mod, that would count as a wrapper method, because you're basically just trying out adding different sets of features. Whereas filter methods, as we were saying a moment ago, basically we have some rank that's generated by something that we then just use that algorithm's output to pick those features. And then there are also embedded methods, which are a little bit more complicated. And I think technically, I think lasso regression would fall under the embedded methods. Let me just confirm that that's true. Yep, embedded methods. Yep. So lasso. So basically, once again, it's generating the subset as it sort of does the modeling. And so that's how ultimately it shrinks those coefficients to zero. Now, this actual lesson, it doesn't actually ask you to code anything below this, but it has a lot of different types of models that it tries, and it prints out a whole bunch of results that, in my opinion, are a little bit hard to kind of digest by scrolling through this page and really appreciate what they're wanting to show us. And so we are going to take advantage of the function that we already wrote together, tweak it just minorly, and be able to actually get all those results that they did from their code already really easily, and actually be able to compare things in a way that lesson does not let us do. So we're going to actually start with our last function as our starting point. And this should only take about another 5 minutes or so. And then, let's get our function. And so it's going to be very similar to this one. We're just going to rename it to match the language of that lesson, because I literally just pasted in the code from that lesson below here. And so, we're going to rename it. And then the other thing is we want the ability to add a note whenever we get a model. So we actually want to be able to build inside of our function the ability to add another column, which we'll do right at the bottom, which we'll just call it note, which is equal to whatever string that we provide in as the note. And you'll notice that we gave it a default of an empty string. That way, it always has something to fill in. That way, it's always going to be present, and there's not going to be no inconsistencies in what it actually generates. And let me double check that there was nothing else we wanted to modify in this. I don't think there was. Yeah, I think we're fine. Yep. Okay. So we now actually, yes, we actually don't need the model anymore. That's going to be one minor difference. Okay. So yeah, we're going to have to go ahead and create the. Oh, what didn't you like? Target equals df. Why did that just error? Oh, did I miss? Oh, yep, there we go. It would help if I loaded in our data just a little bit. Okay, there we go. There we go. So same data the lessons learned working on. They did train tests. They did standard scalar, and then one quick sidebar on something that was confusing for some folks. I got questions about. So it was the way that they did their train test splits. Yeah. So here. So the way they actually did their data, so they basically used iloc to pull out everything except for the one column they didn't want to transform, and then they transformed those features. And then they basically made a data frame wrapped around that transforming that data, and then reset the columns to be the columns that they were from xtrain, reset the index to the index that was from xtrain, and then filled in the variable that they excluded in the first place. And so I just want you to know that is not how you need to do that. So you can actually do that really simply. So we're doing the same thing here. We don't want to include the female column in this. So literally, I just dropped it temporarily and got the columns list. There we go. There are our columns list. And now we're actually just going to go ahead and we're just going to fill in the same xtrain data. We could have made it a copy, but like there's no harm in doing so. So we're going to fit transform our xtrain data and just basically feed in the list of columns we want to transform. And then we're going to fill in those same columns over here. So that means that whatever columns we didn't touch, they're still going to be there. We don't need to add them back. And then so we can basically do what they did in that big cell of code in just those 2 lines right there. So just want to point out that it can be simpler. That might be due to a change in scikit-learn in recent last year or so. Okay, so basically now what we're going to do, so we're just going to have an empty list that we're going to use. And anytime they ran their model, we're just going to wrap an append around it. And so we're going to be able to go through their code and then be able to then show the results and actually start comparing all the things that they do. So they generate polynomial features next, and they want to run a linear regression with polynomial features. And notice we're just giving it a label called poly. And so we're starting to see we still have a better value for our baseline. So then they get into filter methods and basically using a variance threshold method. And basically set up a series of thresholds, and then they basically loop through and use this variance threshold to basically transform the data, do a regression, and then actually get back the models. Now, in this case, we're not going to use our, actually we do. We do use our run model function right here. And then we get our result, and then basically that gets appended. And so we basically concatenate that. This is kind of what we did earlier. This is a lot of data frames being generated in this loop. And all of that just gets added back to our master results list. So now we have all of those in this one data frame. And we can see that our baseline model is actually still best, at least in terms of in the R squared. And they acknowledge, okay, well, that did not seem to eliminate the features very well. It only is a little bit better. So they then employ some other methods. They don't actually talk about these methods. We can definitely revisit them. Basically, they're different scikit-learn methods that are just purposely for feature selection. But we're going to go ahead, run and append those. And then we'll take one last look at these results. And so it looks like, okay, now we're actually starting to get some values that are actually better than our baseline. So it looks like actually the k-best f regression, which was this first option, which used this f regression function from scikit-learn to select the features. And then they go on to test recursive feature elimination, which is a wrapper method. So once again, I'm just appending the results from running that model to our data frame. And basically, I'm now just gonna run the last 2, and then we'll just see all the results final together, and that'll be the end of it for today. So now we're actually gonna use our lasso, and then notice that when we're using lasso, so 2 different, let's see, what was it? Yeah, so one of them is gonna be with our normal X data, one of them's with our lasso with our poly data. So actually, let's fix this legend. This is incorrect. This is lasso for X data, and then this one is lasso for lasso poly. I guess I could have left. Whatever. That's fine. All right, so go ahead and run that one. Run this one, and bam. So here are results, and I just changed out what we're visualizing here. This is a little complicated. I probably should have explained that one. But let's do this. Let me move this up. So this is our results DF right here. So here's just very simple using our highlight min. So it looks like when we look at the error, okay, so actually what's not helpful right now is that we're actually looking at the train and test set data. Now, what's the issue in looking at both of those together and trying to figure out which model is best?
I guess theoretically, you don't really care about the training after it's done. You only really care about what it can do on test data.
Exactly. So what I'm going to do, I'm actually going to go ahead and what we're going to do first, we have the resdf. So we're just going to do resdf.groupby, and we're going to group by the data column. And we're just going to dot get group test. And then we can apply, so let's say test res. Use that. And then now we can do this list line of code with just what we care about and see just the values that are really worth touching. Okay, so actually it does look like the last regression with poly had the, this is the min, right? Yep, the lowest error. And then how do we do when it comes to actually looking at the highlight max for R squared? Okay, so the lasso regression with poly, with polynomial X data, did produce a dramatically improved model that really only got better by 0.02 R squared. But hey, it's an improvement. And so just so you know, the point of this lab they acknowledge here is not necessarily they weren't expecting us to see and show us a crazy improvement in our model, but they wanted us to see all these different ways we could go about actually using feature selection to figure out what features to use. And at least now, the way we did it together, we were able to actually kind of step back and think about them together. Because I don't know about you, maybe it's my ADD, but I could not scroll through this one and really digest what was happening here. It's just too much all over the place. I can't keep it all in mind at the same time. And so that's today's lecture on section 24. So this is so the only thing we didn't talk about today that's inside of the section is generating data. It's a really simple lesson in lab, so I don't think you guys will need much assistance with that. Are there any questions or comments from anything we talked about today? No? All right, well, now I'm going to go ahead and stop the recording.